Hello, I am Sam, and welcome to Science in Space, an intellectual journey through space and time. Today we explore the evolution of a star, from its humble beginnings to its spectacular death. We begin our journey in a stellar nursery, otherwise known as a giant molecular cloud. This vast field of elements, mostly hydrogen, are the birthplace of stars and contain their chemical makeup. Within the clouds are dense regions where elements cluster together. These cloud cores are the beginning of stars. Cloud cores become denser and denser, accumulating in mass until they become a protostar. A large mass formed from the cloud. Protostars become dense enough that the core of them can begin nuclear fusion of hydrogen to helium using the proton-proton change process. At this point, the star is known as a zero-age main sequence star because nuclear fusion has begun. The nuclear fusion continues until the star reaches thermogravitational equilibrium. This means the expanding force of the heat inside the star core has balanced the contracting force of gravity. At this point, the star is a main sequence star. These can range from 0.08 solar masses to 200 solar masses.
Main sequence stars make up the majority of the Hertz-Sprung-Russell diagram. The HR diagram graphs stars' luminosity and mass and helps visualize their stellar evolution. Some stars are not mass enough to start the proton-proton chain. These stars never undergo nuclear fusion and are called brown dwarfs. Brown dwarfs have the mass of about 0.08 solar masses. More massive stars, around 1.5 solar masses, use a fusion process called the CNO cycle, more than the proton-proton chain. This process is dependent on higher temperatures and thus works better in larger stars. Once massive stars run out of the hydrogen in their core, they switch to fusion of hydrogen outside the core of the star. While the core begins fusion of helium to carbon, this increase in temperature forces the star to expand, becoming a red giant. These can range from 0.3 solar masses to 8 solar masses. Red giants are very cool, but due to their large size, they are very luminous. Here's where they fall in the HR diagram. In these stars, helium is converted into carbon in the core using the triple alpha process, a nuclear fusion process. In the most massive stars, larger elements are fused in the nuclear process. This is called heavy element burning. Next, a star can evolve into a number of different things. The Vogt-Russell theorem determines what happens next. It states that the star's evolutionary track is dependent on its initial mass and chemical makeup.
Smaller stars will dim and eventually die as the nuclear fuel in them runs out. These are called red dwarfs and are usually 0.4 solar masses or less. When much larger stars' nuclear fuel runs out, their outer region expands, exposing their dense cores, called the white dwarf. White dwarfs are extremely hot, but dim due to their small size. Here is where they fall on the HR diagram. White dwarfs are extremely dense, but don't collapse further due to electron degeneracy. The dwarf lights up the expelled gas ejected from the star. This is called a planetary nebula. Even larger stars collapse violently due to the force of gravity, then expand quickly, releasing lots of energy. This is called a supernova and is very luminous. Supernovas leave behind neutron stars. These small, dense stars do not collapse further due to neutron degeneracy. A star must have a mass of at least 8 solar masses to supernova. Even larger stars collapse into black holes, an object so dense that light cannot escape its gravitational pull. A star must have a mass of at least 20 solar masses to become a black hole. In review, stars start out as in the giant molecular cloud, where they form protostars. Then they become a main sequence star through nuclear fusion, which evolves into a red giant, which can either end in a supernova, black hole, red dwarf, or evolve into a white dwarf.